Hello everyone, welcome to online class of electrical machines one subject. Previous classes we have seen operating principle, construction, equivalent circuit, phasor diagrams, voltage regulation, process and efficiency of single phase transformers. In today's class, I'll be dealing with the testing of transformers. Under that, we are going to see open circuit, short circuit test, polarity test, back-to-back test, and separation of hysteresis and eddy current losses. So, all this we are going to see in today's class. So, let us do the quick revision of what we have seen in the previous classes. What is a transformer? Transformer is a static device or a static piece of apparatus by means of which electrical power is transferred from one circuit to another circuit without changing the frequency. And it works on the principle of Faraday's law of electromagnetic induction. So this is a transformer having primary and secondary winding. Core will be laminated. To the primary winding, we are applying alternating voltage. Alternating voltage will produce alternating current, and this will set up alternating flux in both primary and secondary windings. So whenever flux is linking with the coil, here EMF is getting induced in the primary, that is self-induced EMF, and the same flux is linking with the second coil also in the secondary side, and EMF will be induced in the secondary, that is mutually induced EMF. And whenever a load is connected across the secondary winding, current will flow in the secondary side also. So this is the entire operating principle of a transformer. Okay, so what is a transformer? It is a static device in which power is transferred from one circuit to another circuit without changing the frequency, and the transfer is happening based on mutual induction between the two circuits and which are linked by a magnetic flux. Construction we have seen. Construction wise, basically for a small transformer there are two parts, winding and the core, but this for a large transformer this will be placed inside a uh, so inside some big material, all this will be placed here. So and then these parts will be taken out, the terminals will be taken out, oil conservator will be there, breather will be there. Okay, so these are the various parts of a transformer for a having bigger capacity. Okay, for high capacity we are going to use this type of transformer. Okay, otherwise for small transformers we don't have outer parts. Okay, just windings and core will be there. Okay, so in all types of transformers, core will be constructed by assembling laminated sheets of steel with minimum air gap between them, and the steel used is having high silicon content and sometimes heat treated to provide high permeability and low hysteresis losses. So these are the various shapes of a sheet steel. EIL, okay, laminated sheets of steel will be used to reduce the eddy current losses, and they are cut in the shape of EIL, and to avoid high reluctance at joints, laminations will be stacked by alternating the sides of joint. That is, if joints of first sheet assembly are at front face, joints of following assembly will be kept at back face. So various components of a transformer are core, windings, insulating oil, transformer tank. Okay, inside this transformer tank, this setup will be put. Okay, oil conservator, breather, cooling tubes, Buchholz relay, explosion vent. Types of transformers as per phase, as per core, as per cooling system. There are various types. So as on the basis of construction, core type, shell type. On the basis of their purpose, step up and step down. On the basis of type of supply, single phase and three phase. And on the basis of their use, power transformer, distribution transformer, instrument transformer. And on the basis of cooling employed, oil filled, self cooled, oil filled, water cooled, and air blast. Transformers we have seen core type and shell type are the two major construction types we have seen. In detail also we have seen about them. See here in this. So basically step up transformer will increase the voltage, step down transformer will decrease the voltage. Construction wise we can see there are two basic parts, magnetic core and windings, and they are placed in the transformer tank and provided with bushings and transformer oil, conservator and all for a transformer of higher ratings. There are two types of windings. One is cylindrical concentric coils, another one is sandwich coils. So cylindrical concentric coils is used in core type, shell and sandwich are used in shell type. Core type transformer we have seen, it is a single magnetic circuit. Core will be rectangular having two limbs. Winding will encircle the core. Coils used are of cylindrical type, and coils are wound in helical layers with different layers insulated from each other by paper. Both the coils will be placed on both the limbs. Low voltage coil is placed inside near the core, while high voltage coil surrounds the low voltage coil. Core will be made up of large number of thin laminations. And this is a shell type transformer. It is having a double magnetic circuit. Core will be having three limbs, and both the windings will be placed on the central limb. So core will encircle most part of the windings. Coils used are generally multi-layered disc type or sandwich coils. So construction we have seen here: core, winding, tank, radiators, bushings, conservator, breather, input leads, output leads, transformer oil. So these are the various constructional features of a transformer. EMF equation we have seen. So EMF equation we got it as 4.44 F phi N1. Phi is equal to phi M is equal to Bm into A, and we have found out the voltage transformation ratio E2 by E1 is N2 by I1, N2 by N1 is equal to K. If you are taking into consideration current also, then I1 by I2 is equal to I1 by I2. Ideal transformer on no load, practical on no load, ideal on load, and practical on load. All these four cases we have seen, and we have seen the phasor diagrams also. What is an ideal transformer? Ideal transformer is one which has no winding resistance, no leakage flux, no iron losses in the core. So this is the phasor diagram for ideal transformer on no load. Then practical transformer on no load we have seen in detail. I have said it in the previous video. Do watch it. Ideal transformer on load, phasor diagrams, three diagrams I have explained in detail. Then practical transformer on load. For unity, lagging and leading power factors, I have shown you the phasor diagrams. Equivalent circuit of transformer we have seen. No load equivalent circuit and equivalent circuit referred to primary and referred to secondary also we have seen. And then equations, various equations, numerical also we have seen. Then voltage regulation. Very important for short question. Voltage regulation is nothing but arithmetic difference between no load secondary voltage and secondary voltage on load expressed as a percentage of no load voltage. So in terms of this I2 R2 cos phi 2 plus or minus I2 X2 is sin phi 2. Secondary if you are considering, primary side if you are considering, I1 R1 cos phi 2 plus or minus I1 X1 is sin phi 2. Positive for lagging power factor, negative sign for leading power factor. Losses in a transformer, only two losses are there, iron and copper. There are no mechanical losses because it is a static device. So iron losses are of two types, eddy current and hysteresis. Their equations, their formulae we have seen. Efficiency of transformer we have seen. Efficiency is output by input or output by output plus losses or input minus losses by input. Condition for maximum efficiency of transformer is whenever copper losses is equal to iron losses, condition efficiency will be maximum. Then we have seen OC and SC test. Efficiency calculated from OC test and SC test as full load volt ampere into power factor by full load volt ampere into power factor plus iron losses plus copper losses. This is full load efficiency. Now if you have to calculate efficiency at any load, multiply this full load VA into X, and the denominator also, numerator also. Iron losses are constant losses, so keep it as it is. Multiply copper losses by X square. Okay, as we can see here, X into full load VA into power factor by X into full load VA into power factor plus PI plus X square PC. So efficiency at any load can be calculated with the help of this formula. Then we have seen OC and SC test on transformer. Rating of transformer. See, rating of transformer should always be in kilovolt ampere, not in kilowatt, because rated transformer output will be limited by heating and hence by losses in the transformer. So two types of losses in a transformer are iron losses and copper losses. Iron losses depend on transformer voltage and copper losses depend on transformer current. And because these losses are depending on voltage and current and they are almost unaffected by the load power factor, so transformer rated output is expressed as volt ampere or kilovolt ampere and not in kilowatt. Very important for short question for 2 marks. This can be asked why transformer rating is in kVA rather than kilowatt. So, so let us continue with today's topic. So we are going to see OCSC test, polarity test, Sumner's test, and separation of eddy current and hysteresis losses. Testing of transformer, OCSC test, polarity, back-to-back or Sumner's test, separation of hysteresis and eddy current losses. So let us start testing of transformer. Introduction. Normally transformers are tested at no load. Transformers can be tested by connecting load to its secondary if its rating is small. Okay, usually for high rating transformer we are not connecting any load and we are conducting the test on no load. So in case of large transformers, it is exceedingly difficult to arrange the large loads enough for direct loading. Also, load test will be associated with a large amount of power wastage. So it is preferred to test transformers without load. So why is it necessary to conduct OC and SC test? It is necessary to know the impedance of the transformer in order to calculate its voltage regulation and efficiency. Impedance and other circuit parameters can be determined by conducting simple no-load tests. So no-load tests have a minimum power loss when compared to that during direct load tests. Let us see the circuit for open circuit test. So for convenience, supply will be connected to the LV side of the transformer and high voltage side of the transformer is left open circuited. Low voltage side, LV side, we are connecting all the meters, ammeter, voltmeter and wattmeter, and we are arranging a variac here, and we are varying the variac till we get the rated voltage in the voltmeter, noting down the values of ammeter and wattmeter, and high voltage side is open circuited here. So apply rated voltage to the LV side of the transformer, measure no load current I0, power P0 and input voltage V0. Measure the open circuited HV side voltage if the transformer ratio needs to be calculated. Now we are seeing the calculation of core losses and magnetizing components. So this is the equivalent circuit diagram we are drawing here. As no load is connected to the secondary, current will flow and the losses due to winding resistance and reactances are very less and they can be neglected, and we are simplifying the circuit as like this. G and B, I, M, I0 is divided into I1 and IM. So, okay, this is an equivalent circuit of transformer. So, neglecting the copper loss, we can calculate the iron losses and core loss components. So, we are going to the wattmeter reading is giving us the iron losses in open circuit test because copper losses are very small and can be neglected. So, P0 is equal to V0 I0 cos phi naught or cos phi equal to P0 by V0 I0. Im is I0 sin phi naught, Ii is I0 cos phi, where Im is the magnetizing current, Ii is the core loss component of current. Core admittance Y0 can be equal to Gi plus JBM. Okay, like how we are having the equation Z is equal to R plus Jx. So similarly, we can write the equation for Y is equal to G plus JB. Also, Y0 is I0 by V0. So conductivity of the core Gi will be equal to P naught by V naught square. Susceptance will be equal to Bm is equal to under root Y naught square minus Gi square. Y naught is the core admittance, Gi is the conductivity of core, Bm is the susceptance of the core. Now let us see short circuit test. The purpose of conducting a short circuit test is to determine the winding resistance, reactance and copper loss of the transformer. Iron losses from OC test, copper losses from short circuit test. So this is the circuit diagram for short circuit test. We are short circuiting the low voltage side, and to the high voltage winding we are applying the alternating voltage through variac. Wattmeter, ammeter and voltmeter are connected. Current through and voltage across we are calculating by varying the variac till we get the rated current. So for convenience, a variable voltage source is connected to the HV side of the transformer and LV side of the transformer is short circuited because voltage required for short circuit test is typically 5% of the rated value. Since the current rating of HV is less than LV, current drawn at 5% of rated voltage of high voltage will be low. At the same time, if we apply voltage to LV winding, current drawn from the supply will be very high. It is difficult to arrange a low voltage high current power source. So we are short circuiting the LV side open and giving the meters to the HV side. and gradually raise the supply voltage from 0 until the transformer draws the rated current. Note down the voltmeter reading, wattmeter reading and ammeter reading, and it can be noted that applied voltage required to circulate current ISC is very small compared to rated voltage of the winding. So whatever the wattmeter reading is showing, it is giving us the value of copper losses. Iron losses are neglected. So excitation current required is too small and can be neglected. So this is the equivalent circuit diagram for a short circuit test. R equal to R1 plus R2, X equal to X1 plus X2. Power input to the transformer measured by PSC corresponds to copper loss. So PSC is Pi square R, VSC is ISC into Z, where Z is equal to R plus JX or VSC by ISC. Resistance offered by the coil R is equal to PSC by ISC square. Susceptance X equal to root of X Z square minus R square. So attained values of R and X will be referred to HV side of the transformer from which the test will be conducted, and it can be referred to the other side using operator A square. Calculation of transformer efficiency. P0 and PSC are the core loss and copper loss of a transformer. So efficiency of transformer can be calculated as kVA rating of transformer by kVA rating of transformer plus iron plus copper losses. If you are taking in percentage, multiply by 100. Next, polarity test. Polarity test will be conducted to find the polarity of the transformer windings. Those ends of the two transformers that acquire positive or negative polarity simultaneously are said to be at similar polarity. So it is necessary to know the polarity of the winding in order to connect it properly. So there are two methods. Let us see the method 1. See here, method 1. One end of the secondary A1 will be connected to an end of the primary winding small a1. Connect voltmeter across other two ends A2 and A2. Now apply a voltage across the primary A1 and A1. If the voltage reading given by voltmeter V1 is equal to V2, then polarities of capital A1 and small a1 is same, and if the voltage is reading V1 plus V2, then polarities of A1 and A2 is same. Method 2. So DC flashing test will be used while the transformer is tested on the field. This method will involve usage of a DC battery of 1.5 to 6 volt and a DC voltmeter. A circuit will be made as shown in the figure, and the battery and the switch will be connected to the HV side of the transformer. So whenever the switch is closed, the end of the LV winding that is at the same polarity as that of HV winding, to which the positive terminal of battery connected becomes positive, and this is indicated by the deflection of the DC voltmeter. So when the switch is opened, similar polarity and acquired negative potential. Next is Sumner's test. Sumner's test is also called as back-to-back test. It is a method to determine the steady-state temperature rise of the transformer. This test is conducted by connecting two similarly rated transformers back-to-back. So this is the circuit diagram for Sumner's test. Two transformers are connected back-to-back. Two ammeters, two voltmeters, two wattmeters and are connected here. So primaries of two transformers will be connected in parallel while the secondaries will be connected in series but in phase opposition such that the voltage across the terminal is 0. So to connect them in phase opposition, polarities of the winding should be known. So polarity test can be conducted if required to know the polarity. Since the secondaries are connected in phase opposition, no current shall flow through it even if they are short circuited, and the current measured by the ammeter A1 will correspond to the core loss component. Similarly, when the primaries are short circuited, full current will flow through the circuit. Current measured by wattmeter W2 corresponds to the copper loss of the transformer. So by conducting Sumner's test, we can calculate iron losses, copper losses without even loading the transformer. So total power input to the transformer will be 2P0 plus 2Pc. Steady state temperature rise of the transformer can be monitored by conducting this test for a longer period and monitoring the temperature rise using a thermometer. Now we will see the separation of hysteresis and eddy current losses. For a sine flux wave, transformer core loss is given as PC is KHF Bm power x plus KE f square Bm square. So I am writing both hysteresis and eddy current losses here. So it can be seen from the equation that hysteresis loss varies linearly with frequency, whereas eddy current losses varies as square of the frequency. So division of both sides of equation by F will give core loss per cycle, that is PC by F. That is equal to KH Bm power x plus KEF Bm square. And now this equation 2 is showing that hysteresis loss per cycle is independent of frequency, whereas eddy current loss per cycle is proportional to frequency. So V is equal to E equal to root 2 pi f n phi max, or V by F can be written as root 2 pi into n phi max, that is root 2 pi n Vm into A, because phi equal to B into A. For any transformer, n AI are constant, therefore Bm is proportional to V by F. For a particular value of V by F, or of maximum flux density Bm, we can write the equation as Pc by F equal to K1 plus K2F. K1 is Kh Bm power x and K2 is Ke Bm square. So equation 3 is a equation of a straight line. Plot of this Pc by F against frequency will result in a straight line. So this is the diagram showing frequency versus Pc by F. And this part is K1 and this is K2F. So values of K1 and K2 can be determined by performing open circuit test on transformer. During this test, applied voltage V and frequency are varied together so as to keep V by F as constant. So we are keeping V by F as constant and performing the open circuit test. In the laboratory, the ratio of V by F can be maintained constant by a DC motor driven alternator feeding the transformer on open circuit. An adjustment of speed of alternator and its excitation will help in keeping the ratio of V by F as constant. So wattmeter driving the open circuit test registers the core losses. Thank you everyone for watching the video. I hope today's class is clear to everyone. Watch the video from start till the end. Give your attendance in comment section. So we have covered the single phase transformers topic. So remaining is three phase transformer, auto transformer, Scott connection, tap changing transformer, three winding transformers. Okay. So we have covered the single phase transformer part of 5th unit. Okay. So remaining one or two classes are required for me to complete your syllabus. So what we have seen in a single phase transformer is a static piece of apparatus by means of which electrical power in one circuit will be transformed into electric power of same frequency in another circuit. It can increase or decrease the value of voltage in a circuit, but with a corresponding decrease or increase in the value of current. So physical basis of a transformer is mutual induction between two circuits which are linked by a common magnetic flux. Transformer consists of two inductive coils which are electrically separated but magnetically linked through a path of low reluctance. And the two coils will possess high mutual inductance. If one coil is connected to a source of alternating voltage, alternating flux will be set up in the laminated core, most of which will be linked with another coil in which it will produce mutually induced EMF. And according to Faraday's law of electromagnetic induction, we can write the EMF equation as E is equal to minus n d phi by dt. If the second coil is circuit is closed, current will flow in it, and so electric energy is transferred entirely magnetically from first coil to the second coil. The first coil in which electrical energy is fed from the AC supply mains is called as primary winding, and the other from which we are taking out the energy is called as, or the energy is drowned out, is called as secondary winding. So in brief, we can tell that transformer is a device which will transfer electric power from one circuit to another circuit. It does so without changing frequency. It accomplishes this by electromagnetic induction and where the two electric circuits are in mutual inductive influence of each other. So when an alternating voltage V1 is applied to the primary, alternating flux phi is set up in the core. This flux will link both the windings and induces EMFs E1 and E2, and E1 equal to minus N1 d phi by dt, E2 is equal to minus N2 d phi by dt. E1 and E2 depend upon the number of turns on primary and secondary windings respectively. If N2 is greater than N1, then E2 is greater than E1, then we are going to get a step-up transformer. N2 less than N1, E2 less than E1, V2 less than V1, step-down transformer. If load is connected across the secondary winding, secondary EMF E2 will cause a current I2 to flow through the load, And a transformer enables us to transfer AC power from one circuit to another with a change in the voltage level. Then we have seen the construction. There are two types of transformer: construction by diffusing, core type, shell type. Then we have seen the construction, each and every part we have seen. So you can check the previous videos. EMF equation also we have seen. So um, average rate of change of flux, that is flux is increasing from its zero value to maximum value in 1/4 of cycle, that is 1 by 4f second. At that time average rate of change of flux is phi n by 1 by 4f or 4f phi m. So average EMF per turn is average rate of change of flux, but to get RMS value multiply average value by 1.11, because for a sinusoidal wave the form factor is 1.11. So RMS value equal to 1.11 into 4f phi m. Then uh, multiply it by number of turns on primary for E1 and number of turns on secondary for E2. So E1 is 4.44 F phi m N1. Because phi m is equal to Bm into A, we are going to get E1 is equal to 4.44 F N1 Bm A. E2 similarly same equation, except that N1 you write here N2. So E1 by N1 is E2 by N2, that is 4.44 F phi m. Voltage transformation ratio, ideal transformer, phasor diagrams we have seen, equivalent circuit. If you have any doubts, you can ask me in phasor diagrams, equivalent circuit, numericals. All of you practice these numericals. Losses we have seen, condition for maximum efficiency, OCSC test, polarity, Sumner's test, separation of iron losses, that is hysteresis and eddy current losses. Thank you everyone for watching the video. Give your attendance in comment section.